All right, well, hey, welcome to another fun-filled week here in trigonometry. Today's plan, we're going to go ahead and cover section 8.3 on the inverse trig functions. And then we'll probably spend a little bit of time talking about the exam that's coming up on Wednesday. So that's what I have on tap. But of course, I like to start with you guys and see, is there anything you'd like to talk about what we were covering previously, or any homework questions? There are some homeworks that's due tonight. All right, well, I'm not hearing anything, and I'm not saying anything in the chat box, which means one of two things. It either means you guys have no questions and everything's making sense and we're liking this stuff, which, well, that's what I hope it means, or it means you just haven't really looked at it yet, which is probably not the best, but regardless, I guess if there are no questions, then I'm going to go ahead and hop up to the whiteboard and we'll start talking about the inverse trig function. So I'll be right back. All right. So where we've been, right, what we've done so far is we've really learned about the trig functions, what the trig functions are, their properties, things like domain and range and all that. We've looked at their graphs, which is awesome, you don't, I don't think, truly understand how much we're going to use the trig functions, or the variety of things where we'll use trig functions. But you'll see that as we go. Obviously, yeah, they came from triangles, but we barely talked about triangles. We're going to continue not really talking about triangles. But anyway, you're going to see the use of the trig functions that goes well beyond triangle measurement. But again, remember what they're doing is we're plugging in an angle and we're getting out a number, and we do use that number to then figure out things like heights of flagpoles and, you know, number of hours of daylight and, you know, whatever, things like that. And that's great. But sometimes we actually want to find the angles when we don't know anything about them, and yet we know everything about sides. So let's just back up a second. Just suppose I gave you this right triangle. All right. So the most famous of them all, the 3, 4, 5 right triangle. And here's my question. My question is, what is this angle up here? We'll call it theta. Okay, so easy question. I just want to know, what is that angle? And, you know, I'll take it in degrees, I'll take it in radians. I'm not really picky. But that's the question, is what is that angle? So really what we have to think about is, what portion of a circle are we rotating through? But that's awfully hard to do. That's an awfully hard thing to actually figure out. We do have tools that help us do that, like a protractor. I'm sure you guys remember using those things back in the day. But that's a physical tool that we can use to help us try to figure that out. And that's basically using the, it's splitting up the rotation with markers. But without one of those, this is actually a really tough question. Okay, well, so what we'd really like to be able to do, though, is, well, think about this angle. Can you tell me the trig functions for it? Like, how about this? What's the sine of theta? What's the value for the sine of theta here? You can type it in the chat box or yell it out.
3/5.
All right, so remember, sine is opposite over the hypotenuse, so it'd be 3/5. So like, we know the sine is 3/5. And I just picked sine, but we also could have said, well, what's the cosine? Well, the cosine is 4/5. The tangent is 3/4, right? And we can find the others as well. But in this situation, we know all of the trig functions. Cool. We know all of the trig functions, but we don't know that angle. So what we really need is a way to get to that angle. Well, that's where the inverse trig functions are going to come. All right. So we're going to define these things, the inverse trig functions, and what their job is going to be is it's going to find an angle given a trig function. I'm going to say one of its trig values or functions. So if you're in a situation like this where you know one of the trig functions, that's what the inverse trig functions are going to do. So these are backwards of what the trig functions do. The regular trig functions, what they did is they took an angle and they gave us some sort of a value. So the inverse trig are going to go backwards. We're going to be given a value and they're going to give us an angle. And that's why they get the name inverse. I don't know if you remember this about inverse functions, but inverse functions are the return trip. They go backwards, right? So great examples of inverses, think about like a square root and squaring. They do the opposite things, right? You take the square root of 25, you get 5. You square 5, you get 25. You're back to where you started. Adding and subtracting are inverse operations. Multiplying and dividing are inverse operations, right? They're going backwards. And so inverse functions are just more broadly defined as they are an inverse of a function is another function that does the reverse. Okay. So that's what we're going to do. We're going to define these things, these inverse trig functions, so that they actually go in the opposite direction. All right, now the way that we're going to write these, the notation we're going to use is this. So for example, inverse sine. We're not going to write inverse sine because that's way too much for us lazy mathematicians. So we're going to shorten it to this. So you'll see there's a little -1 power there attached to the sine. And this piece right here, that's what's telling us that it's the inverse. Okay. So inverse sine, we're going to write sine with a little -1 of x. And all of the other ones are going to be written exactly the same way. You want inverse tangent? Well, it's going to be tangent with a little -1 and then an x. All right, so let me just go ahead and make a list here. So this is what you're going to see for the inverse functions. You're going to see sine inverse, so sine -1, cosine inverse, tangent inverse, and again, so on and so forth. But we'll concentrate on the big 3. So this is the notation that we're going to use. And this should kind of make sense. If you remember inverse functions, if we have a function f of x, then the inverse function is written with the little -1 exponent. So it's exactly the same idea. We're just going to go ahead and specify that it's on the inverse cosine or the inverse sine and so on. So we'll put it on those names. Okay, so that notation shouldn't throw you. It's exactly like what we've seen for inverses before. But I also want to remind you, and you were probably, this should have been mentioned to you when you did inverses back in the day. When we write something like cosine inverse of x, this does not equal 1 over cosine. That is not what that means. This means the inverse of cosine, not the reciprocal. Okay, so just, I'm putting that out there to remind you, don't fall for that. Do not fall for that. This means inverse, not 1 over. Okay. All right, so this is what they look like. Now, there's another name that these sometimes go by. I will never use this. I'll try not to ever use this. Probably the only time I'll ever use this is if I'm like typing something out, because it's a little bit easier to type it out. There's another name for these, and these are called the arc trig functions. So you'll sometimes see arc sine, arc cosine, arc tangent. These are other names for the inverse trig. Okay, so these are just alternate names. So if you ever see that, you ever see arc something, that's just your inverse. This is old. The arc names are kind of older, more traditional. Now we tend to just use the little -1 because it's a little bit. All right, so here's how they work. For example, let's just say we were going to do sine inverse of 1. All right, so how this is working out is it's going to give us an angle. I'm going to go ahead and call this guy just theta for right now. But it's going to give us an angle whose sine is equal to 1. So that means that this is an equivalent statement. I'm going to draw a little like double-sided arrow here, meaning these are exactly the same. This is exactly the same as saying sine of theta equals 1. All right, so can you give me an angle whose sine is 1? Look at your chart, and what do you see is an angle whose sine is 1.
At 90 degrees.
Okay, thank you, 90 degrees. Right, I was about to say, or think about the graph. Think about the graph of sine. Remember, the graph of sine starts at the origin and goes up to 1. So theta is equal to 90 degrees, or I'm going to give it to you in radians because I want to get you guys thinking radians. Right, so theta is equal to pi over 2. So here's what would happen. If you were to do the inverse sine of 1, it's going to spit out pi over 2. It's giving us an angle whose sine was given. All right, so that's how these things play out. It's really just a matter of figuring out what angle gives us that value. All right, so let's try another one here real quick. Let's try, say, tangent inverse of 1. So this isn't sine now, this is tangent inverse of 1. But again, remember what this is asking us to figure out is give us an angle whose tangent is equal to 1. All right, so I want you to look at your chart and tell me an angle whose theta, angle whose tangent is 1. And let's go radians.
Pi over 4.
All right, cool. So pi over 4. But Is there another angle where tangent is equal to 1 on your chart?
I have pi over 4.
Okay, so you go a little bit further down, you see 5 pi over 4. Okay, so we have 5 pi over 4, 5 pi over 4. Okay, well, we could actually keep spinning around in our circle. Turns out there's also going to be one at 9 pi over 4, 13 pi over 4. If we went the other direction, minus 3 pi over 4, minus 7 pi over 4. Dots on here. And so we have like lots and lots of options for angles whose tangent is equal to 1. But this is a problem. Does anybody see why this is a problem, that there's more than one answer? And it all comes down to the definition of inverse function. Like, what makes something a function? What's the key component to some relationship being a function? All this horrible stuff in algebra.
That it has a set value.
Okay, that there's only one value. Yeah. So when we have a function, functions are only functions because when you plug something in, you only get one thing out. There is no option. There's only one answer. And you can see how there's a bit of a problem here, that this isn't actually a function. Because if I just ask you, give me an angle whose tangent is 1, there isn't just one answer. There are an infinite number of answers. And in fact, we have that same problem back here with sine. I didn't go there with it. But same issue. Yeah, pi over 2 works, but so does 5 pi over 2. So does minus 3 pi over 2. So does lots of things. And we're running into an issue here because the trig functions are periodic. The trig functions repeat. The same thing shows up over and over and over and over. So if we're going to say, hey, we're looking for a specific trig value, that's going to happen lots of times. Like in the case of tangent, it's happening every pi. So there's a bit of an issue here. We can't just say, all right, give me an angle whose tangent is 1. Because there are choices. We have to ensure that there's only one value that works. All right, so mathematicians, of course, seeing this and go, well, crap, this isn't a function. Because we're sore losers, because we don't like being told we can't do something. You know what we did? We as a group went, all right, we'll just make it so that it's an inverse. We'll make it so that there's no choice. And the way we're going to do that is by pretty much erasing pieces of the graph. So let me show you what I mean. Let's take the graph of cosine for a second. And cosine, if you recall, actually starts with its maximum at the axis, at the y-axis. So there's a maximum at 1 here. And then it comes down to 0, down to -1, and then so on and so forth. Right? So we're going from 1 to -1, and we just keep repeating. So this is 2 pi. That's pi, just to get some scale on here. Okay, so I'm going to remind you again something else about inverse functions. If you go back and you look at inverse functions, functions only have inverses when they're what we call one-to-one. One-to-one functions are the ones that pass the horizontal line test. So if you draw a horizontal line and it intersects your graph more than once, your function is not one-to-one. And if your function is not 1-to-1, it doesn't have an inverse. Okay, so that's just the thing about inverse functions. And if you look at the graph of cosine, you can clearly see that it's not 1-to-1. I mean, look at the x-axis. It's a horizontal line that intersects this graph more than once. Okay, so here's what mathematicians did. They said, all right, I need to adjust this so that what I have is 1-to-1, and what I have actually has all of the possible outcomes from my trig function. So in terms of cosine, that means I need every number between plus and minus 1. But I need that to only happen one time. So here's what they did. They said, well, let's just erase all the negative stuff, because we definitely don't need that. And then if you look at this graph, it's still not 1-to-1, but let's just start going until we start getting the same y value, the same output. Well, these are new, these are new, these are new, everything is new, everything is new. And then once I hit pi, I start getting things out that I already saw. So what I'm going to do is I'm actually going to end it here at pi. And I'm just going to erase all the rest of this. So if you look at this piece right here actually gives us all of the possible y values, all the possible outputs, exactly once. It's now 1-to-1, passes the horizontal line test. So we're going to look at just this piece right here. And I know for some of you, you're probably going, nah, I don't like this. We're just arbitrarily choosing to eliminate pieces of this. Yep, that's exactly why we're doing it. Well, can we do that? Sure, we can do whatever we want in math, as long as we remember it. Remember that we did things, that we are erasing parts of this graph. Okay? But we can totally do this. And by doing this, we've now created something that has an inverse function. Now, in the language of math, what we did wasn't erase the graph. We restricted the domain. Okay, so we're going to restrict the domain on cosine. We're going to restrict it to 0 to pi. So this new thing, whatever this thing is, whatever you want to call it, a piece of cosine, it's such that its domain is 0 to pi, and its range is still -1 to 1. Oops, including -1 and 1. So we didn't eliminate any of the range of cosine, we just restricted its domain. All right, well, it's this thing that we're going to use to create our inverse function. Okay, so let's start making a little fact sheet about cosine inverse. All right, so some more things about inverses. Inverses swap domain and range. So see these domain and range that we have for our cosine? Those, if we swap them over, are the domain and range of inverse cosine. So inverse cosine, we're going to plug in numbers between -1 and 1. And what we're going to get out are angles between 0 and pi. All right, now by doing this, by putting this restriction on it, we've made it so that it's now a function. So now if you say, what's the inverse cosine of 1? There's one answer, because that only happens one place in this interval. Right? So, for example, what if we were to look at, say, cosine inverse let's go with -1/2. So there are an infinite number of angles whose cosine is -1/2. But we need to find the one that's between 0 and pi, because that's the one that's going to come out. Okay, so you can look at your chart. If you look at the chart, 0 to pi is the top half of the chart. So basically just go down that cosine column and go until you find a place where it's -1/2 in that top half of the chart. So that is one of our nice angles. Can somebody give it to me?
Like the angle in quadrant 2?
Okay, so it's the one that's in quadrant 2, which is going to be,
2 pi over 3.
there you go. So 2 pi over 3. So inverse cosine of -1/2, because of the restriction, because of looking at only angles between 0 and pi, cosine inverse of -1/2 is going to be 2 pi over 3, because that's the only angle in this restricted interval whose cosine is -1/2. And if you look further down on the chart, you'll see another place where it's -1/2. It's not too far from that. If you go down to 4 pi over 3, you'll see that the cosine is also -1/2, but we don't get that one because 4 pi over 3 is too big. It's more than pi. It's not in our interval, so it's not the one that's returned. Okay, so this is total mathematician shenanigans. No doubt about it. We are just kind of willing it to do what we want it to do. But it's totally fine. If all we want is an angle whose trig function value is given, this will work. 2 pi over 3 is that angle. Now, if we want to know all of the angles whose cosine is -1/2, that's another story. This isn't going to do it for us. But this at least gets us one of them. And we're going to see later, when we get to solving equations that involve trig functions, you'll see later how we can get all the rest of them just by knowing the one. Okay, so the fact that we lose all those other ones isn't a problem because we can rebuild them if we want. All right, so there was the restriction on cosine. It's from 0 to pi. We're going to have to play a similar trick for sine and for tangent. Because again, they're periodic, they repeat, they are not one-to-one functions. So we are going to have to restrict them in some way so that we get only one value, so that we can come back to this one with the inverse tangent of 1 and say, okay, which of these infinite number of answers is the one that we get? So let's build the restrictions for cosine and tangent. And seeing we've got tangent on the board, let's look at tangent next. All right, so the graph of tangent. We go back and we look at the graph of tangent. This was the one that had asymptotes every pi on the half pies. So this was pi over 2. There was also one over here, minus pi over 2. Then another one over here, 3 pi over 2, and so on. And then in between, we got that, I don't know what kind of, how I would even describe that shape, but we get these little like branch things, right? All right, so we need to do the same thing. We need to restrict this in such a way that we get every one of the values out at exactly one time. All right, now there are lots of ways we can do this, but the one that was chosen was this. We're going to eliminate everything that's to the left of minus pi over 2, and we're going to eliminate everything that's to the right of pi over 2. So this is where we're going to restrict the domain for tangent. To me, tangent's the one that makes the most sense. I look at that and go, oh yeah, that's perfect. Because if I've got this, I know all the other ones are just copies of it anyway. So let's just use that interval right there. All right, so that means for inverse tangent, we're going to be looking for angles between minus pi over 2 and pi over 2. So let me go ahead and write that up here. So for y equals tangent inverse, now the domain is going to be all real numbers. You can plug in any number you want, but what you're going to get out are going to be the angles that are between minus pi over 2 and pi over 2. And I put parentheses on those because we do not get pi over 2 or minus pi over 2. Those things, the tangent didn't exist for them, right? You look at your chart, tangent of pi over 2, it says UND, it's undefined, or DNE does not exist, or whatever we wrote. So since the tangent of pi over 2 doesn't exist, we can't get pi over 2. All right, but again, just like with cosine, we had to restrict tangent, and the interval that we chose is between minus pi over 2 and pi over 2. But we could have taken any of those blocks, and it would have worked. We could have gone pi over 2 to 3 pi over 2, minus 3 pi over 2 to minus pi over 2. But this was the one that was chosen. And I'll explain in just a second after we see sine why we chose this as our block. Similarly, why we went 0 to pi on cosine when we could have taken all kinds of different intervals. There's a reason that we picked. Okay, so that's what we do for inverse tangent, which is why if you were to say take your calculator and do inverse tangent of 1, you are going to get pi over 4. Because pi over 4 is the one of all those very many angles that's in this interval. If you look at the other ones, 5 pi over 4, way too big. And then 9 pi over 4 and so on. You go the other direction, minus 3 pi over 4, well, that's too small. And all the other ones are as well. So that's the one that we'll get in this interval. All right, so that leaves sine. The question is, what restriction do we put on sine? Well, if we draw a real quick graph of sine, and move my vertical axis over a little bit. So sine starts at the origin, goes up and then comes back down. So does this. And the restriction that we put on to sine is we're going to erase everything to the right of pi over 2 and everything to the left of negative pi over 2. Because this accomplishes the same goal as the cosine. It's getting us every one of these values exactly once. So it is 1-to-1 and it does cover all possible values. Okay, so that means for inverse sine, again, its domain is going to be -1 to 1. You're going to plug in any number you want between -1 and 1. But the angles that come out are going to be between minus pi over 2 and pi over 2. So it looks exactly the same as inverse tangents. It's just inverse sine includes the angles pi over 2 and minus pi over 2, because those are angles that are totally fine with sine. All right, so again, we could have chosen lots of different intervals to do this. But the reason that these were all picked is because these are the intervals that contain quadrant 1 angles. First quadrant angles between 0 and pi over 2. You'll see that the angles between 0 and pi over 2 are in each of these. And the reason those were chosen is those are the angles that come from right triangles. Remember, we're trying to think about the example. The reason I said why we might even care about this was to try to find that angle in the triangle. Well, that's how trig started, right? It all started as trying to solve triangles. And so right triangles are going to be such that you get an angle between 0 and pi over 2. So when mathematicians defined the intervals for these things, they chose intervals that contain first quadrant angles. Had to have 0 to pi over 2. And as soon as you say you want 0 to pi over 2, and you want to attach to it another piece so that you get everything, that forces you to take sine backwards towards minus pi over 2. It forces you to take cosine forwards to pi. And then same thing here with tangent, bring it back to minus pi over 2. All right, so here are your inverse trig functions. Well, at least the big three. The other ones we never use, right? You don't use inverse secant, you don't use inverse cosecant, inverse cotangent, because there's no need. If you're just trying to find an angle, if you know the tangent, you know the cotangent, right? So just knowing one of the inverse trig functions is enough. All right, so basically, it's just going to be a matter of figuring out the angle that gives us the right value that happens to lie in the correct interval. But I'm going to help you out a little bit. Okay, so here are just some things. Okay, if you plug in a positive number into any, this is awesome, any inverse trig function, you always get a first quadrant angle. So you're going to like putting positives into the inverse trig functions because they're just going to give you an angle between 0 and pi over 2. Always. You never have to think with positives. But that's by design. It's totally by design. Right? Like think about cosine. If cosine is positive, you're in either quadrant 1 or 4. Well, these things are designed to give you quadrant 1. All right, so for those, nice and easy. It's when they're negative that you have to pay a little bit more attention. But it's still pretty easy, especially for two of them. Okay, so if you plug in a negative into sine inverse or tangent inverse, you get the negative angle. But for the corresponding positive. So what I mean by this is when we have, say, sine inverse of a negative number, this is going to be negative what we would have gotten if we had done sine of that positive. So let me show you an example. Let's say we're doing sine inverse of -1/2. So this is going to be the same as the negative sine inverse of 1/2. And if you look at your chart, you'll see that sine is 1/2. The first time we run into that is at pi over 6. So this guy is minus pi over 6. So sine inverse of 1/2 is positive pi over 6. So sine inverse of negative 1/2 is negative pi over 6. In essence, that minus sign comes out front. But that's only for sine inverse and tangent inverse. It doesn't work this way for cosine inverse. Okay. Cosine inverse is the only one where you got to think about it. All right, well, anyway, so for negatives, sine and tangent are easy. For cosine, you got to do a little bit of work. That's what it is right here. So if you plug in a negative, into cosine inverse, you get a quadrant 2 angle whose reference angle is the positive result. So this one you're going to have to think a little bit. The others were fast, super fast, super fast. This one, well, it still comes back to what's the positive value angle, but we have to use that as a reference angle. So for example, let's say we were doing cosine inverse of minus 1/2. So here's how you want to do this. Unless you've just got your chart memorized. If you got your chart memorized, cool. You can spit out the answer between 0 and pi whose cosine is minus 1/2. If you don't, here's how you can go about it. And this is what I do mentally. I start with what's the cosine inverse of positive 1/2. So what angle gives me a cosine of positive 1/2? And that one I know is pi over 3. So now I need to go to the second quadrant and think about the angle whose reference angle is pi over 3. Remember that reference angles always come off of the horizontal axis. So if we remember how things are built in that second quadrant, we're going to take pi and subtract pi over 3. So this one is going to be pi minus pi over 3, which is 2 pi over 3. And so that's the inverse cosine of minus 1/2. So cosine's the tricky one here. It's going to be a tricky one when you've got a negative because you're going to have to think reference angle. For sine and cosine or sine and tangent, no problem. Just go to the negative. All right. Well, anyway, this is what they are. And they are used for exactly what I started our question about, or this topic about. So let's go back. And remember the question that I asked you at the very beginning was, given the most famous of them all right triangles, what is this angle up here, theta? All right, well, let's go ahead and calculate this. So what we need is one of the trig values. And it doesn't matter which one. I would prefer it to be one of the big three, since those are the ones we kind of talked about with the inverse trig functions. So since it doesn't matter, I'm going to go ahead and just use sine. So I know the sine of this angle is opposite over hypotenuse, so that's 3/5. So that means that theta is going to equal sine inverse of 3/5. Since I know the sine value, I'm going to use the inverse sine. I'm going to plug 3/5 in, and it's going to give me an angle. Since it's a positive number, that's going to give me a quadrant 1 angle. So it's going to give me an angle that fits in a right triangle. All right, so this is where we're going to have to make use of our technology, because this isn't a nice angle. We don't have this on our chart anymore, right? 3/5 doesn't show up on our chart. So here's where you want to grab your calculator. Sorry, I had to go dig it out of my very messy desk. Okay, so the inverse sine, you should see it somewhere with a sign. I don't know if you can see it on here, but kind of light green is my sine inverse. So whatever kind of scientific calculator you've got, look for the button that has sine. On it should also be one that has inverse sine. Okay, now, the other thing you have to remember is what do we want this, what units do we want this angle in? Do we want radians or do we want degrees? Because your calculator will do it either way. All right, like right now, mine's set up for radians. So if I do the inverse sine of 3/5 and I hit enter, one of the answers I can get 0.643511 dot, 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 dot. And that's in radians. If I wanted it in degrees, obviously I could take that radian and multiply by 180 over pi, right? Or you can make sure that you're in degree mode. So change your, use your calculator or whatever way to change it to degree mode. And in degrees, we get 36 point, I'm going to round it to the nearest 100. It's 36.87 degrees. Okay, so both of these answers are fine. They're both correct. One's in radians and one is in degrees. If you give me the one in degrees, make sure you put the degree symbol on it. If you don't put that symbol, that means radians. So if you're right, just 36.87 without that, that's a very wrong answer. Because I would say it's 36.87 radians, and it's not. It's only 0.6435 radians. Okay, but now we're able to answer that question. We can now figure out what angles are coming from specific trig function values. And that's why we care about the inverse trig. And classically, this is why we care. Functionally, like application-wise, this is the big application of the inverse trig functions. However, mathematically, they're used in lots of other places. They're actually big tools that are used for other things, like you'll see when you get to calculus. So it's important to understand how they behave, not just the numbers that they spit out. All right, but they really are just inverses. They're going backwards. We're plugging in a number and getting out an angle. We just had to restrict the interval. We had to restrict the possible choices of that angle to make them wonderful. Okay, so let's just sort of take stock at this point. How are we feeling about this? Is it making sense what they do and how they work? Any questions? What questions can I answer at this point? I'm seeing thumbs up. I like that. Thanks for that, Robert. We're feeling pretty good. Okay. So let's keep talking about them a little bit mathematically. Just some of the things that happen with inverse functions themselves, not necessarily specifically inverse trig functions. So let's start with this. Do you guys remember what happens if we compose inverses? So if we were to take a function and put it into its inverse or vice versa, does anybody remember what happens there algebraically? And don't you hate this, having to remember stuff from previous math classes in the next math class? I hate to break this to you, but get used to it. Because in calculus, oh my God, all we ever do is algebra and trig. So get comfortable with it now. Do me a favor, for those of you that are going on to calculus, which I think is every one of you. When we're done with this quarter, don't just be like, okay, cool, I'm done with trig, I never have to see it again. Don't approach it that way. Don't study for tests that way. Study this stuff as I want to get this information in here so I can access it later. Because that's going to make calculus so much easier for you. Oh my God, so much easier for you if you've got this stuff down. Anyway, come back to this. What happens when we compose inverse functions? Well, since nobody offered it up, I'm just going to go ahead and throw it out here. They just cancel each other out. And what you get is x. And if you think about what inverses do, this makes sense. Inverses are going backwards, right? So let's just take the trig functions, for example. So let's say we're doing sine of pi over 3. So you plug pi over 3 into sine, you get out a number. You take that number and you put it into inverse sine. It goes to, well, what angle gives you that sine value? Well, that's going to jump you back to where you started. So it turns out that when you compose inverse functions, they just cancel each other out. And what we're going to see is that that also happens with the trig functions. If you take trig and trig inverses, they are going to cancel each other out. All right, so for example, if we were to take, say, cosine of cosine inverse of x, we are going to get x. And the same thing, if we take the cosine inverse of the cosine of x, we're also going to get x. However, we're going to have to be careful here. Because when we built our inverses, we built them off of pieces of the trig functions. So what I can say for sure is that this is going to happen if we have these x's that we're plugging in. So for the first one, this is going to be true, that the cosine and inverse cosine cancel each other out, as long as the x is between plus and minus 1. And the reason that that has to be the case is if you look at the inside of this function, the first piece of the function, we're doing the cosine inverse of that number. And we already saw that the only numbers we can plug into inverse cosine are those between -1 and 1. So if you were to try to plug in like the number 2, it's going to break down because cosine inverse of 2 doesn't exist. That machine breaks before it can even spit something out into the next one. Okay. So this is going to work as long as the x's are between plus and minus 1, which is the domain of cosine inverse. Okay, the other one, the cosine inverse and cosine are going to cancel as long as those x's are between 0 and pi. But if you use your logic, it kind of makes the same, I mean, logically, it's equivalent to the other one. We're only going to be able to do this for numbers that we can plug into cosine. Now, if you kind of been playing along, you go, well, but we can plug anything into cosine. Its domain is all real numbers. Except we restricted it. Remember when we built inverse cosine, we restricted it to these angles. And that's why I only know for sure that this is going to happen if my angles are between 0 and pi. We're going to have to do similar things for when we compose sine and sine inverse or tangent and tangent inverse. But let's look at this for a second, and let's look specifically at an angle that's not between 0 and pi. Okay? So let's do this. Let's look at the cosine inverse of the cosine of 7 pi over 4. So again, you might be tempted, might be really tempted to go, okay, cosine inverse and cosine, they cancel each other out because they're inverse functions. And so our answer is 7 pi over 4. All right, well, like I said, you might be tempted to do that, but do not do that. Because that is wrong. It is not 7 pi over 4. Even if you were to punch this into your calculator, putting cosine inverse and cosine 7 pi over 4, it is not going to answer 7 pi over 4. And that's because 7 pi over 4 is not in the interval 0 to pi. So let's just kind of follow this and see what happens. So cosine of 7 pi over 4, we can calculate. It's on your chart, right? If you go down your chart quite a ways down, 7 pi over 4, it's like the third line from the bottom. And you read over and you see that its cosine is root 2 over 2. So the cosine of 7 pi over 4 is root 2 over 2. Okay, so now we're going to do the inverse cosine of root 2 over 2. So it's going to give us an angle whose cosine is root 2 over 2. But that angle has to be between 0 and pi. It has to be in the top half of our chart. And so if you start at 0 and you start working your way down, you don't have to go very far until you run into pi over 4. So in this case, inverse cosine of 7 pi over 4 is going to be pi over 4. Well, it happens. And it happens because we had to restrict cosine to make it 1-to-1 to even have an inverse cosine. So here's the deal. Right? When we first did it, and I just said, okay, well, we're going to erase all the rest of this, and we're only going to look in this interval. And I'm like, hey, mathematicians do this because we can. Why? Because we can, and we want it, and it works. Every time you do that, though, there are consequences. And this is one of those consequences. I basically just say, when you make an assumption like that, or when you make a restriction like that, where you say, I'm going to look only between these two angles, the consequence to that is that later you're going to have to think. You're going to have to think in circumstances where before you didn't have to. Before, when you ran into inverse functions that were being composed, no thought, they just cancel each other out, you're done. Natural log of e to the x, x. Square root of x squared, x. Right? Like, you didn't have to think about it. Now we have to think. And I apologize, because we don't like doing that. That's when math gets hard, right? And you actually have to pay attention and you have to think about it. It's much easier when we can just turn on the monkey math part of it and just go, oh, monkey math, I just do it, I just do it, I just do it. No, we're gonna have to think about it now when we have inverse functions. The inverse trig functions, because that restriction, don't play the same as the others. They do play the same in the right circumstances, but as soon as you're not in those circumstances, that's where you have to pay attention. Okay, so be careful with these. But remember your restriction on the angles. The restriction on the angles for the inverse trig functions are very important because they even play into this. Okay, so like this is where the inverse cosine and cosine will play nicely. For sine, they're similar, right? If we do the sine inverse of x, that will equal x, but that's going to equal x again when x is between -1 and 1. For the same reason, there's only things we can plug in inverse sine. But then if we do inverse sine of x, that's only going to work when those x's are between -pi/2 and pi/2. That was the restriction that we made on sine just to even have an inverse. So similar thing's going to happen. If we were to, let's just take one here. Let's do sine inverse of sine of, let's say 4pi/3. Because 4pi/3 is not in this interval, we can't just cancel those out. Instead, we think about where is sine, or what is the sine of 4pi/3? Well, if you look at your chart, you go down your list, sine of 4pi/3 is minus √3/2. Okay, so now we need the angle between -pi/2 and pi/2 that gives us minus √3/2. Well, let me remind you the little trick I told you about putting negatives into inverse sine and inverse tangent. We're going to pull that minus sign out front. And so the question is, where in the first quadrant is sine equal to √3/2? Well, that's pi/3. So the inverse sine of the sine of 4pi/3 is minus pi/3. So again, they don't cancel out. We actually get a different value, but that was because of the restriction that we put on sine in the first place. So again, apologize on behalf of mathematicians. You're gonna have to think here. Yeah. But you got a pretty awesome brain. Use it. Use it. Okay, so there are the restrictions for sine. And then lastly, for tangent, it's very similar, as I'm sure it's not going to surprise any of you. But if we were to look at the one for tangent, the tangent of tangent inverse, that's going to equal x. And again, this one though is nice. This works for all x. And that's because inverse tangent, its domain was all real numbers anyway. So that one's good. If you do the tangent inverse of tangent of x, again, there is a restriction on this. And it's the x's that are between -pi/2 and pi/2, not including the endpoints. So those are strictly just greater than and less than symbols. But that's due to the exact same reason. The restriction on the tangent to make the inverse even exist. Okay, so there's a reason I'm bringing this up, and it's not just because. It's going to be later when you're solving equations that have trig functions, and they show up a lot in that real world. But when you've got an equation with a trig function, the way you get rid of that trig function is with one of the inverses. You do this kind of composition. But we're going to have to remember that that restriction was going on. And so we're going to have to take that into account to find the others, because we may not even be getting the value that we specifically are looking for because of that restriction. Okay, so this is something you need to file away for. Yeah, we're going to need this. And in not too long, I think we're going to hit solving trig functions probably, well, for sure, sometime in May. So solving equations with trig functions, we're definitely going to need to make use of it. All right, so hopefully you're kind of okay with this, at least seeing the why we have to pay attention. Okay, it all stems back to the we erased everything but a small chunk of the original trig function. All right, but then we can have mixed composition. And what I mean by mixed composition is what instead of taking the cosine of the cosine inverse, what if I take the sine of the cosine inverse? Or the tangent of the cosine inverse? Or the sine of the inverse tangent? Or, right, we can actually do all sorts of combinations of these. And so I want to address a little bit about how this works. Okay, so this is going to be mixed composition. And an example, we'll just throw it right out here at the start. Let's say we're doing, say, the sine of cosine inverse of root 2 over 2. Okay, so this is the kind of thing that I'm talking about, right? Or say the tangent of sine inverse of 1/3, right? Or insert your favorite. We'll do one more here. How about cosine of tangent inverse of 37? Okay, so that's the kind of thing that I'm talking about. All right, now with mixed composition, there's never going to be, yeah, those things just cancel each other out. Okay, I shouldn't say never. There are going to be times where the answer ends up being the same, but that's purely coincidental. Okay. But in general, these things don't just cancel each other out because they're different kinds of functions, right? It's like if I were to say take the square root of a natural log, that doesn't mean they cancel each other out, because square roots don't cancel logs, exponential functions, right? Or logs don't cancel square roots, squares do. So you got to have the right matchup for them just to go away. All right, but even though we can't just cancel them out, it is still possible to calculate these things, to find out what numbers we get if we just sort of follow the process and see what happens. So let's start with this first one, where we've got sine of cosine inverse of root 2 over 2. And I chose a value that was nice. It's going to lead to an angle that we know. So let's sort of follow what's going to happen here. We're going to start by figuring out the inverse cosine of root 2 over 2. So that's going to be an angle somewhere between 0 and pi, whose cosine is root 2 over 2. Well, since it's positive, we know it's a first quadrant angle. And in the first quadrant, where cosine equals root 2 over 2 is pi over 4. All right, so this is asking us then, what is the sine of pi over 4? Well, again, we know that angle. Its sine is root 2 over 2. So the sine of the inverse cosine of root 2 over 2 is root 2 over 2. This is one of those very rarely occasional spots where they do cancel out, but total coincidence. All right, so easy enough when it's when it gives us an angle that we know. I mean, and that was the kicker, is that this thing led to the angle pi over 4 that we know and love. We know everything about it. We can get its value. All right, so let's look at this next one. Right? So this next one, we're going to start with inverse sine of 1/3. Don't bother looking at your chart, because we don't have an angle whose sine is 1/3 anywhere on our chart. Okay? But it is going to be an angle, right? It's some angle, and this is an angle whose sine is 1/3. And this guy theta is somewhere between minus pi over 2 and pi over 2. Okay? But we know that the sine is equal to 1/3. So if we can calculate that theta, then what we're looking for is the tangent of that theta, right? Okay. Well, you know what? You've already done that. Oh, I know what you're thinking. But Bruce, this is the very first day we've talked about inverse functions. What do you mean we've already done that? Well, you remember those homework problems that said, here is the value of one of the trig functions. Find the values of the other ones. In fact, I'm pretty sure you had some on the quiz. This is exactly that. Right? This is basically saying, given that sine of theta equals 1/3, find the tangent of theta. So you remember how to do this? I mean, there are a couple of different approaches. Probably the easiest is with the right triangle. Okay, so here's theta, and I know that sine is 1/3. So my opposite side is length 1, and my hypotenuse is length 3. I want to find the tangent, which means I need to find my adjacent side. So we go to our Pythagorean theorem, a squared plus 1 squared equals 3 squared, which gives us a is the square root of 8. So then if we go to the tangent of this thing, the tangent is opposite over adjacent, which is going to be 1 over the square root of 8. So there's a reason why we had you do those problems. Given one trig function value, find the others. Because we use that when we do this mixed composition. All right, so that's really all that's going on with mixed composition, is given one trig function value, find the other. That's it. It usually entails drawing a right triangle. You can also use the identities to do it if you want, right? Like given a sine, we can calculate a cosine from the Pythagorean identity. Then we can take the sine and divide by the cosine to get the tangent. I prefer just to draw the right triangle. So with the mixed composition, I highly recommend that you write it this way, that you take whatever that interior one is and write it as a trig function. Not the inverse trig function, but the trig function itself. To help you remember what you know. This is telling me my angle has a sine of 1/3, which means I know it fits on this triangle. And once I know that one, I can get all the rest. All right, so I had another example up there. Let's just do that one real fast. So we were looking at, I think it was the cosine of the inverse tangent of 37. But same story. This tells me that my tangent of theta equals 37. I want to know what is the cosine of theta. So I'm going to draw my right triangle. Tangent is opposite over adjacent. Now, I don't have a fraction. I have just 37. But remember, you can make any number a fraction. You just slap it over 1. So I've got 37 and 1 as those two sides. But if I want cosine, I need to know the hypotenuse. Okay, well, from the Pythagorean theorem, we're going to have 1 squared plus 37 squared equals c squared. And I have no idea what 37 squared is. Let me just get that really quickly. It's 1369. So adding 1 gives us 1370. So c is the square root of 1370. Oh, okay. So then what's the cosine of this angle? Well, cosine is adjacent over hypotenuse. So this is going to be 1 over the square root of 1370. Rationalize it if you feel like. All right. So that's the deal with mixed composition. Is it's exactly what we'd been doing when it was given one trig function. Yeah. Okay, but I do have to give you, I've given you really easy examples. And you might look at this and go, didn't seem like this was that easy. No, these are easy because we're just plugging in positive numbers. And the reason positive numbers are fine, let's just think about it. Inverse trig functions, every one of them takes a positive and gives us a first quadrant angle. And then when we calculate the trig value of a first quadrant angle, always going to be positive. So everything's always positive. Positive, 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 positive. You have no worries. Negatives are a different story. Okay. Negatives are a different story. So let me show you what happens when we throw in a negative inside of one of these things. So let's just do, say, the cosine of the inverse sine of minus 2/5. Okay, so again, what we know, or what we're basically told here, is that we're given sine of theta equals minus 2/5. Find the cosine of theta. So now here's kind of the issue. Let me just start by thinking about this. Let's go to the good old quadrant picture here. So inverse sine of -2/5. We're looking for a place where sine is equal to -2/5. That actually can happen in two places, right? Sine can equal -2/5 in either quadrant 3 or quadrant 4. Remember your good old all students take calculus. All of them are positive here. Sine is positive there, and then it's negative in these two. And the reason that this is a potential issue is think about cosine in those quadrants. In quadrant 3, cosine is negative, and in quadrant 4, cosine is positive. So just knowing that the sine is equal to -2/5 isn't actually going to be enough for us, because I still don't know if cosine is positive or negative. Okay, so now you're starting to see why we got to pay attention with the negatives. But there's good news. This isn't all we know about it. In fact, you should be able to tell me which quadrant this angle is in, because there's only one choice. And I'll give you a hint. We're dealing with inverse trig functions. So which quadrant is this angle going to be in? Quadrant 3 or quadrant 4? Think restrictions. What were the restrictions on sine to even make an inverse happen? What angles were we between?
-pi/2 to pi/2.
Okay, so we were between -pi/2 and pi/2. So -pi/2 is down this way. Pi/2 is up this way. So inverse sine only ever gives us angles in here. Quadrant 1 or quadrant 4. And since it's negative, that tells me I'm in quadrant 4. So when you do the mixed composition, if there's a negative, you have to pay attention to what quadrant you're in. But you'll know what quadrant you're in by using the restrictions. For tangent and sine, you're in quadrant 4. We're going down to -pi/2. For inverse cosine, you're going to be in quadrant 2. You go from 0 to pi. All right. So again, remember I said there are always consequences to the playing these shenanigans, mathematical shenanigans. Here's another one. When we do the mixed composition, specifically with negatives, we have to pay attention to where we are due to that restriction. All right, well, this is actually good. So we know a little bit more. We know the sine is -2/5, but we're also in quadrant 4. And so since we're in quadrant 4, I know that my answer is going to be positive. So I like to do this just at the very beginning. I put a plus or a minus sign right away, because I know where I know what my value is going to be, depending upon where I am. Cosine is positive in quadrant 4. All right, then what I do is just draw the right triangle. I do what we did before. So here's my right triangle. Here's a theta. I know that its sine is 2/5. Now I don't worry about the negative anymore. The negative I took care of by figuring out what quadrant I'm in. So now I'm just going to go and use the positive values. So sine is opposite over hypotenuse. So I can go ahead and find my a here, doing the same thing as before. A squared plus 2 squared equals 5 squared. So a is the square root of 21. So then cosine is adjacent over hypotenuse. So that's the square root of 21 over 5. And again, I know it's positive because the inverse sine of the negative brought me to the fourth quadrant, and cosine is positive in quadrant number. Okay, so with negatives, still build the right triangle the same way, do your calculations. You just use that negative to figure out where you are. So that then you can determine the sign, plus or minus sign, on the other trig. So here's another one. Let's do the tangent of the inverse cosine of minus 5/6. So first things first, let's figure out where we are. Okay. So we know the cosine of theta is equal to minus 5/6. And again, we're trying to figure out what is the tangent of theta. Well, let's figure out what quadrant we're in. So what quadrant is theta in? So use your tool.
Would that be quadrant 3?
Okay, so quadrant 3. What do you guys think? Is cosine negative in quadrant 3?
Yeah, either 2 or 3. but
Okay,
I don't know.
So since it's negative, we know we're in either quadrant 2 or 3. So which one are we for sure in? And unfortunately, I think that was you, Robert, who said that first. It's not quadrant 3. It's quadrant 2. And why it's quadrant 2 is the restriction on cosine for the inverse cosine. What was our restriction? What angles could we use for inverse cosine?
Is between 0 and pi?
Okay, so they were between 0 and pi. So think about where that is. Here's 0, and there's pi. So for inverse cosine, we're trapped in either quadrants 1 or 2. Negative cosine is either quadrant 2 or 3, which put those together tells me that this is in quadrant 2. So that's the thought process that you want to take on. You want to think about what quadrants give me the right plus or minus sign, and then which of those is in the restriction for the given inverse. Okay, so since we're in quadrant 2, I know that the tangent is going to be negative. So I'm going to go ahead and put a little minus sign there, because I know that this answer is going to end up being a negative number. All right, well, let's figure out what that negative number is. So we'll draw a right triangle. We know the cosine is 5/6. So cosine is adjacent over hypotenuse, which means I still need to find the opposite side, but we'll use the good old Pythagorean theorem to find that. And that gives us that b is the square root of 11. 36 minus 25 is 11, right? B is the square root of 11. So tangent is opposite over adjacent. So it's going to be the square root of 11 divided by 5. So the tangent of the inverse cosine of minus 5/6 is negative root 11 over 5. And there you go. Okay, so mixed composition. It is what it is. And just trust me, this is going to be useful later. It's going to be really useful later. And in fact, when you get to second quarter calculus, so Math 106 next winter, you're going to learn this thing called trig substitution, which is a technique for doing integrals. And this is going to show up a lot. So it's not going to go away. So practice it now and get it done now. But just realize that all we're doing is given one, find the others. We already know how to do that. This just now has that added little twist of pay attention to where you are. And of course, that makes everything worse. Okay, so there is inverse trig functions. Just take them for what they are. They're going backwards. They are now given a trig value, find the angle. And in terms of their applications, that's where we're going to use them, is every time we want to find an angle. We'll see plenty of it over this quarter. But we still have a little bit of time left. Looks like we got about like 15 more minutes. So I'm going to hop back down to my computer and we're going to talk a little bit about the exam that's coming up on Wednesday, things to know, and what I'm going to expect from you. Okay, so I'll be right back with you. All right, so exam on Wednesday, our first exam. First of all, in terms of the topics, the chapters that are being covered, it's all of chapter 7, which was the introduction to all the trig functions and all that. And then 8.1 and 8.2, which was about really the trig functions and their graphs, so their properties and their graphs. So it's going to be those sections. In terms of things that you should know how to do and things that are going to be important here. If we just start at the beginning, for sure know how to convert between degrees and radians, right? That's kind of a big deal. Know about standard position, like, and what all the different things mean for angles. So, you know, the initial side, the terminal side, know what it means for angles to be coterminal, the reference angles, all the different quadrants, things like that. So basically just know that the geography of the world, of the trig world. And then the other thing that we talked about in that first section were some of those rotational quantities. So things like areas of sectors of circles, arc lengths of circular arcs, their relationships between the angles and all that. So like S equals R theta, A equals 1/2 R squared theta, that kind of stuff. And then also know the difference between, say, like linear velocity versus angular velocity. Linear velocity is like you think of like speed, distance over time, or angular velocity is angle over time. But we definitely care about that when we talk about rotation. So 7.1 was all about really just setting the table with angles and the idea with the rotation. Then we started getting into the trig functions themselves. So know your trig functions in terms of their definitions with right triangles, the good old SOHCAHTOA, kind of like what we were just doing here, where if you're given some sides of a triangle, you can figure out the different trig functions. But then we extended that to the unit circle. So also know their definitions in terms of the unit circle, using the coordinates of the point on the unit circle. But I want to remind you that if you're given a point that's not on the unit circle, you can't just use those X and Y.
right? You actually have to scale it back by your distance away, so the radius of the circle. That's why the unit circle is better. Honestly, if you have a point on the unit circle, you're done. You can just read off the coordinates. The x is your cosine, the y is your sine, and then go from there. So know their definitions on the unit circle. And then in there, we also hit the relationships between all the trig functions, all those sort of the basic identities that we've run into, the reciprocal, the fact that that three of them are just reciprocals of the others. So I call them the big three, right? The fact that co-functions are related to each other. We had the co-function identities. We had the quotient identities, which told us about how tangent and cotangent are built from cosine and sine. And then we had the Pythagorean identities. The big one there is sine squared plus cosine squared equals 1. And then there were a couple of variations on that, right? There was the tangent squared plus 1 equals secant squared, and the 1 plus cotangent squared equals cosecant squared. But those really came from the fact that they were on a circle, and the Pythagorean theorem holds and all that. So kind of interesting mathematically, I think, to see that right triangles and circles are really mathematically structured the same. Anyway, so we talked about the identities, and then we hit all of these special angles. So review your chart, know how to use your chart. Obviously, since this is a take-home kind of test, since you're doing it at home, I can't expect that you have that chart memorized, but I'm just going to tell you it is in your best interest that you get that memorized, that you know those things, because when we return back to quote unquote normal and we're back on campus, just so you guys know, when you take a calc test, I know that both Larry and I, Larry Green's the other calculus teacher, so depending upon who's teaching it, it'll be one of the two of us. But I'll tell you that we both expect that you know, like the sine of pi over 4 is root 2 over 2. Not that you're going to look it up, that you know those numbers. Okay, so there is going to be that expectation going forward that you know that chart. Now, while you don't have to have that thing really memorized and down in depth right now, realize that you're going to need to do that eventually. Anyway, so know the special angles. Hopefully you're starting to get a little bit comfortable with radians, because I tend to just do everything in radians. I want to prep you for calc, but you know, if you need to do the conversions, that's fine. So know the chart. It definitely helps you see the relationships. It also tells you things like the signs, the plus or minus signs in the different quadrants, right? So know those. Basically, just know the properties of the trig functions. And that's what chapter 8 was really about, was looking at all the properties of them. So know things like their domain, their range, the intercepts, whether they're even or odd, because they're all of them are either even or odd, right? So know those kinds of things, be able to replicate their graphs, be able to, like if I were to give you the graph of some sort of sinusoidal wave, be able to give me the equation of it. So be able to kind of go backwards, be able to figure out periods and amplitudes and phase shifts so that you can reconstruct it, right? So specifically with the graphs of sine and cosine, know those three things: amplitude, period, and phase shift. So amplitude is how far we're going up and down from the center line. Period is how long it takes until we repeat. And then phase shift is how far we've been shifted over. And when we talk about that, think about shifted over from the y-axis. So a cosine, its maximum is usually at the y-axis. So if we've been shifted over, that's going to be your phase shift, is however far your max went. For sine, since it's the midline, right, you're going in the midpoint that's going through the origin, you're looking for how far did that middle move, left or right. I think it's a little bit easier to see shifts on cosine than sine. One of the reasons why I like cosine better. But anyway, so be able to, if I give you an equation, be able to determine amplitude, period, and phase shift, and use that to help kind of draw the graphs. And like I said, be able to go backwards. There are also some on the homework, if you've run into them yet, maybe you haven't, where they'll tell you something like, the temperature in the day varies sinusoidally, and the high temperature is 55 and the low temperature is 35. Create the equation, right? That's kind of the same deal where you're given the information. Can you go backwards? For things like that, the period is usually going to be inferred. It's not going to be explicitly stated, right? So like if it's something daily, your period is 24 hours. If it's something annually, your period is 365 days, right? So things like that. But just think period is how long it takes until it repeats. And from the context of the question, you should be able to figure that out. All right, so know how to do that with those. And then with the like secant and cosecant and tangent and cotangent, be able to draw the graphs, be able to recognize the graphs. But again, they're not quite as useful in the real world as sine and cosine. Yeah, so that's the kind of stuff that you need to know for this exam. It will be a lot like the quizzes, just more, right? Imagine putting quizzes together and then another quiz for the other stuff. And so it's basically gonna be like that. So in terms of how it's gonna play out, we are not having class on Wednesday. Okay, there's no in here Zoom time on Wednesday. That time is test time, just as if we were in class. So just like with the quizzes, the exam is going to open at 11 o'clock. You'll be able to access it on Canvas the same way. You're just going to go to exam 1 and you should be able to get the link. And then I believe I have it set that it needs to be uploaded by 1:30. Not entirely sure that that's the number, but I think it is. It says on Canvas what time it needs to be uploaded by. So basically it's a 2-hour test and wiggle room for technology. It shouldn't take anybody that long. It really shouldn't. Yeah, don't push it. Please upload it onto Canvas, preferably as one PDF. Makes it way easier. If you upload it as a picture for every single page, that's kind of a pain. It will still work, but I would prefer it just as a single PDF if possible. And if you're having any trouble getting it uploaded on Canvas, immediately email it to me. Okay, and as long as that time is relatively close to the due time, I will still call it good, right? So if it's, I got it, I emailed you at 1:36. Okay. I emailed you at 2:14. Yeah, not okay. All right. So in a pinch, don't hesitate to send me an email. I will be around. I'll probably start in our room, in our, actually, I'll just have our Canvas room open. So if you have any questions, you can pop in. Just realize that I might be, not there right away, but as soon as I get back, I will answer your question and let you know what's going on. So I'll still be around if you have questions. It's just we're not having class. All right. Okay, so I think that's everything I need to share about the exam. Do you guys have any questions at this point? Other than that angst of not knowing what to expect exactly?
I had a question about a few of the homework problems.
Okay, we don't really have time to do that right now because class is about to be done. But let's see, I don't have office hour later today. I do have office hour tomorrow if you can pop in, Robert. If not, send me an email and we'll find a time where we can get together. I just have a class immediately after this, so I don't have time right now.
For sure, sounds good.
Okay. All right, any other questions?
Do you know how many questions are on the test?
306. No, I have no idea. And I know I get asked that question all the time, which is why I always respond with some outrageous number like that. So here's always my question with someone who asks that. Is it going to change how you study if I were to tell you that there were 30 questions versus 5 questions? That's a
No.
legit question. No, probably not, right? So I think I say that as a way to get, maybe that's not something that you should worry about in general with exams. You know, yeah, I know that at the time, then you might be like, oh my God, there's like, I don't have enough time to do it or whatever. If that even ends up being the case, I still would say don't worry about it until you're confronted with it, because otherwise you're going to have all that angst and it's going to distract you from the studying and all that. And honestly, I have no idea how many questions are going to be on there. I don't even want to tell you a number, because if I say, oh, there's going to be a dozen, and then it turns out that there's 14, people are going to be like, oh, you said there were only going to be 12. But, you know, but Danielle, honestly, I have no idea. And it really shouldn't affect how you study. So just roll with it when it happens.
Mhm.
I'll just tell you, in my experience, exam 1 in Trig, time is never an issue for anyone. So the number of questions I put on there is never such that it's going to, you know, take you forever. And again, 5 questions versus 15 questions. I mean, you either know the stuff or you don't, right?
Mhm.
So, but anyway, do you like my way of avoiding that answer?
Is good.
Yeah.
All right. Thank you,
Yeah,
Bruce.
don't stress about how many exam questions. Just know the material and you'll be good. All right. So with that, I'm just going to wish you guys good luck, even though you don't need luck. Study and you'll be good. And I will see everybody in class a week from today. All right. So have an awesome week, or until the next time I see you.
Thank you very much. You too.